Hello, my name is Lee Hansen. I'm a Senior Manager for Xilinx Processing Technical Marketing, and today I'll be discussing the Xilinx SDSoC Development Environment. For this quick take video, I'll first talk about the challenges to implementing a system in a Zynq SoC device, and how SDSoC helps solve those challenges. Then I'll give a demonstration of SDSoC on an example design, first to generate a quick performance estimate to understand the achievable acceleration possible for my design. Then afterwards, running a full design implementation using those estimate settings and verifying the results achieved on an evaluation board. When designing an SoC architecture, engineers must carefully choose how best to implement the functions within their design. Does the system run best with functions implemented in hardware or running in software? And once a function is selected to be implemented in hardware, what is the best interface and driver to handle the data movement between the processor and the hardware? When targeting a Xilinx Zynq 7000 SoC, we can implement functions either in software on the processors or in hardware on the FPGA programmable logic, using multiple hardware data movers like DMAs and FIFOs, with 3 different types of interfaces for moving data between the PL and the PS. That results in at least 16 possible configurations to optimize for per function, which would take days and weeks to explore using traditional embedded design methodologies. The SDSoC development environment provides a greatly simplified ASSP-like programming experience with the industry's first C and C++ full system optimizing compiler. SDSoC delivers system-level profiling and automated software acceleration from a single framework, unlike traditional separate hardware-centric and software-centric flows, which can result in multiple iterations to reach an optimized system. SDSoC delivers even more productivity through rapid system performance estimation. Users can specify which functions to consider for acceleration in programmable logic. And SDSoC instruments the C and C++ code to report software cycles and estimates for the data transfer as well as overall application speedup. SoC implementation goes from days and weeks down to minutes and hours. For today's demonstration, I'll use a Zynq ZC702 board. The ZC702 is an ideal embedded evaluation platform that contains a Zynq 7020 device containing dual ARM Cortex-A9 processors, and Zynq peripherals like USB 2.0 and Ethernet enabled on the board, and 85,000 equivalent logic cells of FPGA to house your design's hardware logic. This is the SDSoC interface. Installing the platform gives you a complete front-to-back implementation environment for your Zynq designs, either on Linux or Windows. Starting a project is very easy. I just give it a name. Remember, I'm evaluating on the ZC702 board, but SDSoC comes with support for a number of pre-built Zynq platforms like the Xilinx ZC706, Avnet's Z or MicroZ boards, or Digilent Zybo board. And SDSoC also supports adding user-defined platforms. I can attach an OS like Linux or FreeRTOS or run standalone bare metal. And SDSoC also includes a number of pre-built source templates for functions like matrix math or filters like FirFilters. These can either be added to an existing project, or you can create a project from scratch using the templates. SDSoC is a full C and C++ code development, debug, performance estimation, and measurement framework based on Eclipse. In the top left is the Explorer window. I've got a design ready to start. Note my hierarchical directories like my include libraries and my source libraries here. In the center window, is where I edit and debug C and C++ source code, and where reports will be generated and displayed. The window includes a context-sensitive editor that helps me interactively edit and create and check source code. The outline window on the right displays an ordered list of all my header and function calls in the currently open source code. At the bottom left is the target communications window. SDSoC includes a complete hardware connections engine based on TCF, or the Target Communications Framework. The connections engine auto-discovers the board I'm connected to via USB and also supports remote debug, so you can run remote evaluations on a board anywhere in your network, such as a lab environment. The center window, the lower center window, shows me my console window for implementation messages, so I see how implementation proceeds, the build proceeds. I also have a problems window for warnings and errors, and more is here as well. We'll see it as we progress. And finally, my console log for connections. Along the top is an ordered set of commands for functions like programming the board or generating the boot image. And again, we'll see more of those commands as we progress. This demonstration project contains 3 C++ functions that by default have been set to implement in software and then run on the processors. Which brings me back to the original problem. How should I best implement these 3 functions, either in hardware or software, to give me the best overall SoC performance? I'll start by exploring what the performance difference would be by accelerating the matrix math functions, the matrix adder and the matrix multiplier. Note the H's indicate these 2 functions are scheduled to implement now in hardware or logic. I can also open up the SDSoC hardware functions directory to see it keeps a running total of the functions that have been assigned to implement in logic or hardware. And now I'll set the build configuration to estimate mode. Estimate gives me very fast results because I have fewer compiler options, I have few implementation steps. I don't need to go through and generate the FPGA bit stream or the boot images. It runs much faster. And now, first I'll toggle the console window on, and now I'll build the design. The estimate is done. Note in the console window that the build took a little over 2 minutes, about 2.5 minutes to complete. And I now have an estimate that shows accelerating the matrix adder and the matrix multiplier will result in about 58,000 cycles in hardware. It also shows me an estimate of the resources those 2 functions will take up in the FPGA logic: DSP, block RAM, lookup tables, and flip-flops, what they will use versus total available. Also note that SDSoC generated an executable file in ELF. I can use this click here link to execute that file, connect to my board. The log file will tell me that the board gets reset, the FPGA gets programmed, my CPU is run, and now that's complete. So, again, for the matrix adder and the matrix multiplier, now I have a software-only measurement estimate of 183,000 cycles. And again, our hardware accelerated estimate of just over 58,000 cycles, or a speed up of 3.1x. From the top level, from the main function, I'll get a speed up of about 1.5x. You can set the performance estimate function to anywhere in the hierarchy you want. So if you need to optimize on subfunctions, you can do that. So now I've been able to quickly explore and generate an estimate of accelerating 2 of my functions from the C++ source. Now I want to fully implement this design. So I'll close that. I'll change the build configuration to debug. Debug will give me a complete implementation flow, including generating an SD card image boot files, the FPGA bitstream, application executable files, all of those. And now we'll re-execute the build. The full implementation build is complete, and checking the console window, I see that took just over 30 minutes to run on this laptop. I can scroll through the console window to see all the implementation steps, when they were executed and what their status was. If there had been errors or warnings, they would show up in the problems window. In this case, there were none. And before I run this implementation on my board, I'd like to show you another report that the debug configuration generates called the Data Motion Network Report. This is a very vital report to SDSoC, and it shows me, in this case, the two matrix functions that have been accelerated into logic, the matrix adder, the matrix multiplier. It shows me their arguments, their I/O. It also shows me the interface ports that'll be used between the processing system and the programmable logic in the Zynq 7000, and shows me the data mover that will be used to communicate data between the hardware and software. In a follow-on video, we'll use this report to further optimize this design. Now, the debug configuration also generated an SD image directory, and it includes all the files and directories I need to boot on my board. So I'll copy that over to a blank SD card I have located in my laptop. And then I will take that card out and load it into my board. Now, before I reset the board, I'll also show you SDSoC contains a number of useful windows for debug. One of those is the terminal window. In this case, I've preset it to COMS4 on my laptop to the correct baud rate in serial mode. And now the terminal window is connected to the Zynq 7000 UART output. So as my board output progresses, that'll be shown to me in SDSoC. There's no need to separately have to load a terminal program like Hyperterm or TerraTerm. Everything you need for debug is here. So now we'll power on reset the board. I'll watch the progress as Linux boots. And once Linux is done, I'll CD over to the /mnt directory where the executable files are located. And there's my ELF executable file. We'll run that. That runs our main C++ program, and the output shows that the average processor cycles measured for this implementation is just under 93K. Remember, our estimate was 58K, so we've greatly accelerated over the 183K for full software. But there's still some room for optimization. Join me in a follow-on video, and I'll show you how I can optimize this design even further. As we've just seen, the SDSoC Development Environment provides a greatly simplified ASSP-like programming experience with the industry's first C and C++ full system optimizing compiler. I demonstrated that in just over 30 minutes, I've estimated the performance increase for accelerating two C++ functions into hardware, then turned around and fully implemented that design on the evaluation board. And I drove implementation for both the hardware logic and the software from the C++ source. In a follow-on video, I'll look at even more optimization options for this project and how SDSoC also supports interactive debug of my project. For more information, go to Xilinx.com, and thank you for your time.